In this video, we provide more results of our work. Our method is the first real-time physics-aware approach that estimates human motion, joint torques, and ground reaction forces solely from 6 inertial measurement units. The sensors are placed on the forearms, lower legs, head, and pelvis. We perform a calibration before capturing the motion, which only requires the actor to stand in T-pose for a few seconds. We first present the real-time demos. The entire system is run on the laptop, and the screen shows the real-time reconstruction results. The estimated ground reaction forces are visualized by the red lines. Note the systematic delay is only 16 milliseconds, while sensor I/O and model rendering add a bit more latency. Different from vision-based methods, ours is not limited by occlusions. In this demo, the subject successfully returns to the starting position in a round walking. It demonstrates that our system stably captures the global translation with very little accumulated error. We also capture a real working scenario to demonstrate the capability of our system to track very long and still motions. As the inertia measurements for sitting still and standing still can be very similar, it is considerably ambiguous and challenging to track a sitting motion stably. Our system successfully captures the subject for half an hour with very little drift. The system even works pretty well after the tracking when the subject stands up. In the following, we present more evaluation results. We first demonstrate our force estimation by visualizing the estimated limb joint torques in red. As shown in these examples, the shoulders generate larger forces when the arms accelerate since arm movements are controlled by the shoulder joints. In this motion, the left leg produces larger torques than the right leg as it needs to support the whole body. In this jumping motion, the ground reaction forces increase at the beginning to accelerate the body, disappear after the jump, and reappear in the landing. Next, we demonstrate our proposed learning-based RNN initialization strategy. The method without the learning-based initialization fails to track a sitting pose as it forgets the state change signals from standing to sitting. In contrast, our complete method captures the sitting faithfully. This is because the learning-based RNN initialization helps to capture and memorize the crucial state change signals. Finally, we show the effect of our dual proportional derivative controller. The method without the dual PD controller estimates a more jittery and unbalanced motion. In contrast, our complete method looks much more natural due to the global pose control introduced by our proposed controller. In the following, we compare our method with the state-of-the-art ones. We first focus on the estimated pose. Notably, our method achieves higher pose accuracy than previous works. We then focus on the full motion estimation. Our method outperforms the previous state of the artwork in translation accuracy and motion smoothness. Finally, we present some failure cases. We first show a very rare and ambiguous pose. As a data-driven method with little input information, our approach is incapable of such poses. In this case, our method fails to capture walking onto the chair due to the mismatch between the unknown real-world environment and the flat ground plane assumed in our system. Our approach enables applications such as gaming and real-time character animation. Thank you for watching.